Hi viewers. Now in this session we are going to do chi-square test. Chi-square test has three subtopics, that is chi-square distribution, chi-square test of independence and chi-square goodness of fit test. So let's start with chi-square test, what it is and what are the different types of chi-square test, etc. So, as a researcher, when we are testing the hypothesis, this chi-square test can be one of the hypothesis testing. So, once we start this topic, the first question that comes to our mind is, what is chi-square test? A chi-square test is a hypothesis testing method, and two common chi-square tests involve checking if observed frequencies in one or more categories match expected frequencies or not. So, one question that may strike to your mind is chi-square test the same as like what we write as chi-square test? So, in Greek symbol, it is chi. Okay, so that X represents as chi. So we call it as chi-square test also. So yes, it is same. So what are my choices? Like why should I go for it? If you have a single measurement variable, you use a chi-square goodness of fit test. If you have two measurement variables, then you use a chi-square test of independence. There are other chi-square tests, but these two are the most common. So as I have already told you, the two types of chi-square test, that is chi-square goodness of fit test and chi-square test of independence. And both these tests involve variables that divide your data into categories. So as a result, people can be confused about which test to be used. Okay, so but the basic idea behind this test is to compare the observed values in the data to the expected values that we will see if the null hypothesis is true. So let's compare the two tests. So like if we see in chi-square goodness of fit test, number of variables is 1, while on the other hand, chi-square test of independence, number of variables are 2. Then if we see the purpose of test, so chi-square goodness of fit test decide if one variable is likely to come from a given distribution or not. While in the chi-square test of independence, the purpose of test is to decide if two variables might be related or not. Example, for chi-square test of goodness fit is decide if bags of candy have the same number of pieces of each flavor or not. While an example for chi-square test of independence can be to decide if moviegoers' decision to buy snacks is related to the type of the movie they plan to watch or not. Okay, so in both the cases, let's see the hypothesis. Hypothesis in null hypothesis for the case of the goodness of fit example which we have taken can be that the proportion of flavors of candy are the same. So this is the null hypothesis. While the alternate hypothesis says that proportions of flavors are not the same. While in chi-square test of independence, the hypothesis, that is the null hypothesis, will be proportion of people who buy snacks is independent of the movie type. While in alternate hypothesis, we can have the proportion of the people who buy snacks is different for different types of movies. Another point of difference is degrees of freedom. For we can say in chi-square goodness of fit, a number of categories is calculated like -1. Okay, so like in our example, number of flavors of the candy -1 will be the degree of freedom for the chi-square goodness of fit test. While for chi-square test of independence, like we are saying number of categories for the first variable minus the -1. So multiplied by the number of categories for the second variable -1. So in our example, number of movies that is the category -1 multiplied by 1. So because snack purchase is a yes or no variable, and so the degree of freedom will be 2 minus 1, that is 1. Now, how to perform a chi-square test? So, for both the chi-square test, that is the goodness of fit, and the test of independence, we can perform same analysis steps. First step is to define our null and alternate hypothesis before collecting our data. So after putting on the first step, we decide on the alpha value. Already we have discussed so much about the alpha value in our t-test and z-test. So this involves deciding the risk you are willing to take of drawing the wrong conclusion. So for example, suppose we have to set alpha at zero point zero 0.05 when testing for independence. Here you have decided on a 5% risk of concluding the two variables are independent when in reality they are not. Then we have to check the data for errors. That is the third step. Then in fourth step, we'll check the assumptions for the test. And for this, we have to see the assumptions first. And fifth step is to perform the test and draw the conclusions. I will be taking the assumptions in further slides. So both chi-square tests, we can say, involve calculating the test statistic. The basic idea behind the test is that we compare the actual data values and what would be the expected if the null hypothesis is true. So the test statistics involves finding the square difference between the actual and the expected data values and then dividing the difference by the expected data values. And for this, each data point and then taking up and adding up the values. So then we compare the test statistics to a theoretical value from the chi-square distribution. And then the theoretical value depends on both the alpha value and the degrees of freedom for our data. Now, coming to what is chi-square test of independence. Now, this chi-square test of independence is a statistical hypothesis test used to determine whether two categorical or nominal variables are likely to be related or not. When can I use the test? You can ask me this question at this moment. Yes, you can use this test when you have counts of values for two categorical variables. You can ask me again, can I use the test if I have frequency counts in a table? Yes, you can. So if you have only a table of values that shows frequency counts, you can use this test. Now using the chi-square test of independence. So chi-square test of independence checks whether two variables are likely to be related or not, that you need to keep in mind. So we have counts for two categorical or nominal variables. Now we also have an idea that the two variables are not related, that is our hypothesis. The test gives us a way to decide if our idea is plausible or not. So what we will do in this test, we will do one example, we will run the test, we will understand the results, and we will see the statistical detail, and then we will be understanding the p-values. Now, how do we go for the test? So for the chi-square test of independence, we need two variables, and our idea is that the variables are not related. The assumptions which I told you, I'll be discussing with you. So here are a couple of examples which I'm going to take for the test of independence. Like suppose we have a list of movie genres, and this is our first variable. Our second variable is whether or not the patrons of these genres bought snacks at the theater. So our idea is, in a statistical term, on our hypothesis is that the type of the movie and whether or not people bought snacks are unrelated. So the owner of the movie theater wants to estimate how many snacks to buy if movie type and snack purchases are unrelated. So estimating will be simpler than if the movie types impact snack sales. Another example can be a veterinary clinic has a list of dog breeds they see as patients. Now, the second variable is whether owners feed dry food, canned food, or a mixture. So, our idea is that dog breed and types of food are unrelated. So if this is true, then the clinic can order food based only on the total number of dogs without consideration of the breeds. Now, for a valid test, we need three things. One is data values that are simple random sample from the population of interest. Another is two categorical or nominal variables, and we don't use the independence test with continuous variables so that we define the category combinations. However, the counts of the combinations of the two categorical variables will be continuous. Now, each combination of the levels of the two variables, we need at least five expected values. So when we have fewer than five for any one of the combination, the test results are not reliable. Let's take a closer look at the movie snack example. Suppose we collect data for 600 people at our theater. For each person, we know the type of the movie they saw and whether or not they bought snacks. So let's start by answering, is the chi-square test of independence an appropriate method to evaluate the relationship between movie type and snack purchases? We have simple random sample of 600 people who saw a movie at a theater. We meet this requirement. So our variables are the movie type and whether or not snacks were purchased. So both variables are categorical. So we meet this requirement also. The last requirement is for more than five expected values for each combination of the two variables. To confirm this, we need to know the total counts for each type of movie and the total counts for whether snacks were bought or not. So for now, we assume we meet this requirement and we will check it later. It appears that we have indeed selected a valid method. Okay, so here is our data. As you can see, movie type is action, comedy, family and horror, and the snacks purchased is 50, not purchased 75. Those who saw comedy, one out of that 125 purchased and 175 did not purchase. Those who were watching the family drama, out of that 90 purchased, 30 didn't purchase. And then those who were watching the horror movie, 45 purchased and 10 did not purchase. So before we go further, let's check the assumption of five expected values in each category. The data has more than five counts in each combination of movie type and snacks. So what are the expected counts if movie type and snack purchases are independent? Now, finding the expected counts, we find the expected counts for each movie snack combination. We first need the row and the column totals. So we see snacks 310, and for no snacks it is 290. Then action movie it is 125. For comedy movie it is 300. For family movie it is 120, and for horror it is 55. So grand total is 600. The expected count for each movie snack combination, they are based on the rows and columns total. So we multiply the row total by the column total and divide by the grand total. So this gives us expected count for each cell in the table. For example, action is next cell. So we have 125 into 310 divided by 600. So answer comes to 65. So we rounded the answer to the nearest whole number. If there is not a relationship between the movie type and snack purchasing, we would expect 65 people to have watched an action film with snacks. So here are the actual expected counts for each movie snack combination. In each cell of the table, the expected count appears in bold and the actual count. So you can see the expected counts are rounded to the nearest whole number. So as you can see in the table, the numbers are with bold. So when using software, these calculated values will be labeled as expected values or expected cell counts or something like that only. Some similar term will be there. Now, all the expected counts of our data are larger than 5. So we meet the requirement for applying the independence test. Now, before calculating the test statistic, let's look at the contingency table again. The expected count use the rows and columns total. So if you look at each of the cells, we can see that some expected counts are close to the actual count, but most are not. So if there is no relationship between the movie type and snack purchases, the actual and the expected count will be similar. So if there is a relationship, the actual and expected count will be different. A common mistake with expected count is to simply divide the grand total by the number of cells. So by our movie data, this is 600 upon 8 is equal to 75. So this is not correct. So we know the row totals and the column totals. These are fixed and cannot change for our data. And the expected values are based on the row and column totals, not just on the grand total. So now performing this test, so we need to do the calculations. As we can see, the basic idea in the calculating the test statistic is to compare actual and expected values. Now, given the row and column totals that we have in the data, first we calculate the difference from the actual and expected for each movie snack combination. So then next we square the difference. Squaring gives the same importance to the combinations with fewer actual values than expected and combinations with more actual values than expected. So next we divide by the expected value for the combination. We add up these values for each movie snack combination and this gives us our test statistic. But this is much easier to follow using the data from our example. So here in the table which is there on the screen shows the calculations for each movie snack combination carried out to two decimal places. Now to get our test statistic, we add the numbers in the final row for each cell. Here you can see I have added it and it comes to 65.03. Now, to make our decision, we compare the test statistic to value from the chi-square distribution. So, in order to do this, we have to involve five steps. Now, the step one, we decide on the risk we are taking to take off concluding that the two variables are not independent when in fact they are. So for movie data, we had decided prior to our data collection that we are willing to take 5% risk of saying that the two variables, movie type and snack purchase, are not independent when they are really independent. So in statistics terms, we speak in the significance level alpha to be 0.05. So we calculate a test statistics and our test statistic is 65.03. We find the critical value from the chi-square distribution based on our degrees of freedom and our significance levels. So this is the value we expect if the two variables are independent. Now the degree of freedom depend on how many rows and how many columns we have. So degree of freedom, as we have already seen, row minus 1 into column minus 1. So df is equal to, this is a formula. So here we have four rows and two columns. So 4 minus 1 is 3 and 2 minus 1 is 2. So 2 minus 1 is 1. So 3 into 1 is 1. So we have 3 degrees of freedom. And for the second one, like we have, it is 3 degrees of freedom only. So the chi-square value with alpha 0.05 and 3 degrees of freedom is 7.815. So we compare the value of our test statistics, that is 65.03, to the chi-square value. That is, so since 65.03 is greater than 7.815, we say that movie type and snack purchases are independent. Now we conclude that there is some relationship between movie type and snack purchases. So the owner of the movie theater cannot estimate how many snacks to buy regardless of the type of the movies being shown. So instead, the owner must think about the type of the movie being shown when estimating the snack purchases. It's important to note that we cannot conclude that the type of the movie causes a snack purchase. The independence test tells us only whether there is a relationship or not. It does not tell us that one variable causes the other. So we need to understand through the use of the graphs to understand to see the test results. Now, the charts also shows that the actual count in blue and the expected count in orange. So the count appears at the top of the bars. The yellow box shows the movie type and the snack purchase totals. These totals are needed to find the expected counts. So here we have seen in the graph as with the numbers and the colors differentiation and comparing them with the expected and the actual accounts for the horror movies. Okay, so we can see that more people than expected bought snacks and fewer people than expected chose not to buy snacks. So if we look across all four of the movie types and whether or not people bought snacks, we can see that there is a fairly large difference between actual and the expected counts for most combinations. The independence test checks to see if the actual data is close enough to the expected counts. That would occur if two variables are independent. Now, even without a statistical test, most people would say that two variables are not independent. The statistical test provides common way to make the decision so that everyone makes the same decisions on the data. Now, the chart here, as you can see, which shows the expected and the actual counts using different sample data about the movies and the snacks purchased. Okay, so we can see from this data set that exact same row and column totals for movie type and snacks purchases, but there is yes or no splits in the snack purchases are different. Okay, so the purple bar, which you can see show, let me point out, this purple bar shows the actual counts in this data. And the orange bar shows the expected counts, which are the same as in our original data. So the expected counts are same because the row totals and the column totals are same. Now, looking at the graph, okay, most people would think that the type of the movie and the snack purchases are independent. If you perform the chi-square test of independence using this new data set, the test statistic is 0.903. The chi-square value is still 7.815 because the degrees of freedom are still 3. So we would fail to reject the idea of independence because 0.903 is less than 7.815. So the owner of the movie theater can estimate how many snacks to buy for each type of the movie, which here we are shown in the four categories, that is the action, comedy, family, and the horror. So let's see what are the statistical details underlying this example. So as we have seen, and we look back to the movie snack data and the chi-square test of the independence. Okay, so our null hypothesis is that the type of the movie and snack purchases are independent. The null hypothesis is written as HO, movie type and snack purchases are independent. The alternative hypothesis is the opposite. That is, movie type and snack purchases are not independent. So before we calculate the test statistic, we find the expected count, which is written as you can see over here, EIJ is equal to RI into CJ upon N, or I can highlight it. It is this one. N is the total number of observations. So the formula is for IXJ contingency, that is I into J contingency table, that is table with I rows and J columns. So for example, E11 is the expected count for the cell in the first row and the first column. The formula shows Ri as the row total of the ith row and Cj is the column total of the jth row. So the overall sample size is n. So we calculate the test statistics using the formula OIJ minus, you can say EIJ whole square upon EIJ. So in this formula, we have n combinations of rows and columns. The summation symbol means to add up the calculations for each combination. Now we perform these same steps in the movie snack example in the beginning, and the formula shows OIJ, that is the observed count for the ith, IJth combination, and EIJ is the expected count of the combination. So for movie snack example, we had 4 rows and 2 columns. So we had 8 combinations. We then compare the test statistic to the critical chi-square value corresponding to our chosen alpha value and the degrees of freedom for our data. So using this, our chi-square value is written as like this. I'm highlighting it. It is chi at point 0.5 comma 3. So that is the degree of freedom. So there are two possible results for our comparison. The test statistic is lower than the chi-square value, or the test statistic is higher than the chi-square value. So if it is lower, we fail to reject the hypothesis of independence. Now, in the movie snack example, the theater owner can go ahead with the assumption that the type of the movie a person sees has no relationship with or whether or not they buy snacks. Now, once it is higher than the chi-square value, in that case, we can reject the hypothesis of independence. Like we can say, the movie snack example, the theater owner cannot assume that there is no relationship between the type of the movie a person sees and whether or not they buy the snack. So here we can see it in the diagram. Okay, we fail to reject the hypothesis of the independence if the test statistic is smaller than 7.815. Okay, because only 5% of the distribution is under the curve to the right of 7.815. So we reject the hypothesis of independence. So if the test statistic is larger than 7.85. Okay, so understanding this graph of chi-square distribution, we need to understand the p-values also. Okay, so graph shows, as I have already told you, it shows the value of 7.815 cutoff, that is 95% of the data, and only 5% of the data from the chi-square distribution with 3 degrees of freedom is greater than 7.815. Now, the next distribution graph shows our results. So here we can see how far out in the tail our test statistic is. So as we can see in the tail, okay. Uh, Now with this scale, if we look to the distribution curve at 0 point, we intersects with our test statistic. Okay, so it isn't, but is very, very close to 0. So we can conclude that it is very unlikely for this situation to happen by chance. The results that we collected from our movie goers would be extremely unlikely if there were truly no relationship between type of the movie and the stamp purchases. So here we will be using statistical softwares which will show the p-value for the test. We won't calculate it manually. Okay, we will be using softwares. So, but predicting the value of p. Okay, so it's difficult to calculate this by hand. So for distributions, we will take the test statistic is exactly 7.815 and the p-value will be 0.05. With the test statistic of 65.03, the p-value is very, very small. So in this example, most statistical software will report the p-value as p is less than 0.0001. This means that the likelihood of finding a more extreme value for the test statistic using another random sample and assuming that the null hypothesis is correct is less than one chance in 10,000. So this is what is the we can see from the graph also. Okay, the chi-square distribution plotted for 3 degrees of freedom, and we are just examining it. Okay, then understanding what is chi-square goodness of fit test. This is also one very important parameter in chi-square test. So, chi-square goodness of fit test is a statistical hypothesis test used to determine whether a variable is likely to come from a specified distribution or not. It is often used to evaluate whether sample data is representative of the full population or not. So now one question may arise in your mind, when can I use this test? Of course, you can use this test when you have counts of values for a categorical variable. You may also ask me one question, is this test the same as Pearson's chi-square test? Yes, it is same. Now using the chi-square goodness of fit test. So this chi-square goodness of fit test checks whether your sample data is likely to be from a specific theoretical distribution. So we have a set of data values and we have an idea, that is our hypothesis about that data value distributed. So this test gives us a way to decide if the data values have a good enough fit to our idea or if our idea is questionable. So what do we need to do carry out this test? For the goodness of fit test, we need one variable. We also need one idea or what we call it as hypothesis. So about this variable is whether it is distributed or not. So here I am coming up with a few examples with you. So as I was talking to you about the examples, let's take for the first example. Like we have a bags of candy and 5 flavors in each bag. Now the bag contains an equal number of pieces of each flavor. Now the idea we would like to test is that the proportions of the 5 flavors in each bag are the same. Now another example we would like to take for a group of children's sport teams. We want children with a lot of experience, some experience and no experience, shared evenly across the teams. So suppose we know that 20% of the players in the league have a lot of experience, 65% have some experience, and 15% are new players with no experience. So the idea we had like to test is that each team has the same proportion of children with a lot, some or no experience as the league is a whole, you can say identity. Now, to apply the goodness of fit test to a data set, we need number one, data values that are a simple random sample from the full population. Another thing which we need is categorical or nominal data so that the chi-square goodness of fit test is not appropriate for continuous data. This thing we need to keep in mind. A data set is required that is large enough so that at least 5 values are expected in each of the observed data categories. Now coming to the fitness tests example. As I have spoken to you, this example of bags of candy, so that I will continue further. Let's use this bag of candy and we collect a random sample from 10 bags. Each bag has 100 pieces of candy and 5 flavors. Our hypothesis is that the proportion of the 5 flavors in each bag are the same. So let's start by answering. Is the chi-square goodness of fit test an appropriate method to evaluate the distribution of flavors in the bags of the candy? We have a simple random sample of 10 bags of candy. We meet this requirement. Our categorical variable is the flavors of the candy. So we have the count of each flavor in 10 bags of the candy. So we meet this requirement also. Now each bag has 100 pieces of candy and each bag has 5 flavors of candy. So we expect to have equal numbers of each flavor. So this means we expect 100 upon 5, that is 20 pieces of candy in each flavor from each bag. So for 10 bags in our sample, we expect 10 into 20, that is 200 pieces of candy in each flavor. So this is more than the requirement of our 5 expected values in each category. So based on the answers above, yes, the chi-square goodness of fit test is an appropriate method to evaluate the distribution of the flavors in the bags of candy. Now, as we can see from the bar chart of the counts of the candy flavors from all 10 bags, like these 5 flavors are apple flavor, cherry flavor, grape, lime, and orange. So without doing any statistics, we can see that the number of pieces for each flavor are not the same. Some flavors are fewer than the expected, that is 200 pieces, and some have more. But how different are the proportions of flavors? Are the number of the pieces close enough for us to conclude that across many bags there are same number of pieces for each flavor? Or the number of pieces are too different for us to draw this conclusion? Another way to phrase this is to do our data values to give a good enough fit to the idea of equal numbers of pieces of candy for each flavor. To decide upon, we find the difference between what we have and what we expect. Then to give flavors with few pieces than expected the same importance as flavors with more pieces than expected. And then we square the difference. Next, we divide the square by the expected count, sum those values. This gives our test statistics. So let me tell you by doing it. So these steps are much easier to understand. Okay, so let's start by listing what we expect if each bag has the same number of pieces for each flavor. So we calculated this as 200 for 10 bags of candy. Okay, so here in this table, you can see uh, number of pieces of candy, 10 bags, and expected number of pieces of candy. So expected is same for all the 5 flavors, that is 200, 200, 200. And actual were 180, 250, 120, 225, and 2. Okay. So now we find the difference between what we have observed in our data and what we expect. So we can see over here in this observed minus expected. Okay, so 180 minus 200 is minus 20. 250 minus 200 is 50. Likewise, we'll calculate it. Okay, and then what we will do, we will square it. So what we do over here, uh, we square it. Okay, so here you can see and then squaring the difference over here. Okay, so 200 minus 20 becomes 400, minus 50 becomes 2500, likewise. Okay, so now once it is squared, next we divide it by squared difference upon the expected number. So what was the expected number? 200 for each, so we divided by 200 each and we get a value. That is what is our test statistic. Okay, so to draw the conclusion, we compare the test statistic to a critical value from the chi-square distribution. We first decide on the risk we are willing to take for drawing an incorrect conclusion based on our sample observation. So for the candidate data, we decide prior to collecting data that we are willing to take a 5% risk of concluding that the flavor counts in each bag across the full population are not equal when they really are. So in statistics, we say that it is the significance level, that is alpha. Alpha, that is 0.05. That is what we have taken. So we calculate the test statistic and our test statistics comes to 52.75. As you can see, I have done the calculation also here. You can see in the table. all these values are added up. Okay, so 2 plus 12.5 plus 32, okay, plus 3.125 plus 3.125. So this is all equal to 52.75. Okay. So next step will be we find the theoretical value from the chi-square distribution based on our significance level. Then the theoretical value is the value we would expect if the bag contains the same number of pieces of candy for each flavor. So here we have the degree of freedom, that is n minus 1. N is our 5. That means 5 flavors we were taking. So 5 minus 1 is 4. So degrees of freedom is 4. Chi-square value alpha is 0.5 and degrees of freedom is 4. So we will write over here it is 9.488. So we compare the value of our test statistic, that is 52.75, to the chi-square value. So since 52.75 is greater than 9.488, we reject the null hypothesis that the proportions of flavors of candy are equal. So we make a practical conclusion that bags of candy across the data, we can say it does not contain equal number of pieces for the 5 flavors. So this makes sense if we look at the original data. So if our favorite flavor is lime, you are likely to have more of your favorite flavor than the other flavors. If your favorite flavor is cherry, you are likely to be unhappy because there will be fewer pieces of cherry candy than you expect. So here we can see the actual count of pieces of candy in 10 bags through the bar chart with blue bars you can see over here. So now another sample bar charts, we can see that the expected counts of 200 per flavor. So this is what our chart would like if the bag of the candy had an equal number of pieces. So we are having equal, that is 200. Okay. But here in this chart, I have given you the actual versus the expected. So actual was expected was 200, but actual was some less, sometimes more, sometimes less, and sometimes. So here this side by side chart also shows the actual observed number of pieces of candy in blue, and the orange bar shows the expected number of pieces, actual one. So we can see that some flavors have more pieces than we expect and some flavors have fewer pieces than what we expected. Now, this statistical test is a way to quantify the difference. So, is the actual data from our sample close enough to what is expected to conclude that the flavor proportions in the full population of bags are equal or not? So, from the candidate data above, we have seen that most people would say the data is not close enough even without a statistical test. So, what if your data look like the sample in figure 5, so which is below? Okay. Uh, so the purple bar shows the observed counts and the orange bar shows the expected count. Some people would say that the data is close enough, but others would say it is not. So the statistical test gives a common way to make a decision so that everyone makes the same decision on a set of data values. Let's look at the candidata and the chi-square test of goodness of fit using the statistical terms. So this test is also known as Pearson's chi-square test. Our null hypothesis is that the proportion of flavors in each bag is the same, and we have 5 flavors. So the null hypothesis is written as H0 is equal to P1 is equal to P2 is equal to P3 is equal to P4 and P5. So likewise, we can see like the formula above uses P for the proportion of each flavor. So if each 100-piece bag contains equal number of pieces of candy for each 5 flavors, that the bag contains 20 pieces of each flavor. This proportion of each flavor is 20 upon 100, that is 0.2. The alternative hypothesis is that at least one of the proportion is different from the others. So this is written as HA, at least one P is not equal. Okay. So in some cases, we are not testing for equal proportions. Look again at the example of the children's sports team near the top of this, you can say, session. So using that as an example, our null and alternative hypotheses are H0 is equal to P1 is equal to zero point 0.2, P2 is equal to 0.65, and P3 is equal to 0.15. And HA says at least one P is not equal to expected value. So unlike other hypotheses that involve a single population, we cannot use just a formula. So we need to use words as well as symbols to describe our hypothesis. So here we can now do the calculation for the test statistics and use the formula, that is summation is equal to OI minus EI the whole square upon EI. That means outcome minus expected का whole square upon the expected. So now in this formula we have n groups. So the summation symbol means to add up the calculations for each group. So for each group we do the same steps in the Candy exam. The formula shows OI as the observed value and the EI as the expected value for a group. Now we then compare the test statistic to a chi-square value with our chosen significance level, which we also call as alpha level. So the degrees of freedom for our data, as we know, will be n minus 1. So using the Candy data as an example, we set alpha to be 0.05 and have 4 degrees of freedom. So for Candy data, the chi-square value will be written as chi-square subset of 0.05 comma 4. There are two possible results from our comparison. The test statistic is lower than the chi-square value, or the test statistic is higher than the chi-square value. So if it is lower, then we fail to reject the hypothesis of equal proportions. We conclude that the bags of the candy across the entire population have the same number of pieces of each flavor in them, and the fit of the equal proportion is good enough. But in case if it is not, that means the test statistic is higher than the chi-square value, we reject the hypothesis of equal proportions. And we cannot conclude that the bags of candy have the same number of pieces of each flavor. So the fit of equal proportion is not good enough. So we can use a graph of the chi-square distribution to better understand the test results. We can also check if our test statistic is more extreme value in the distribution than the critical value. Okay, so the distribution shows a chi-square distribution with 4 degrees of freedom, and it shows the critical value of 9.488, cuts off at 95% of the data. That means only 5% of the data is greater than 9.488. So as we can see in the graph, okay, chi-square distribution with 4 degrees of freedom, and the area in green, as you can see, I can highlight this area is the area where we fail to reject the hypothesis of equal proportion, okay, and only 5% of the distribution is under the curve of the right of 9.45488, okay. So we reject the null hypothesis of equal proportion, and if it was greater than 9.488. Now here we can see again the chi-square distribution with 4 degrees of freedom. Okay, so if the data is here lying in this proportion, okay, so we reject the hypothesis of equal proportion. Okay, and the test statistic is 52.75. So now let's see where it is lying. So as with this scale, it looks as if the curve is at 0. Okay, and here we can see as it is very close to 0. Okay, So we conclude that very unlikely for this situation to happen by chance. The true population of bags of candy had equal flavor counts. So we would be extremely unlikely to see the results that we are collected from our random sample of 10 bags. So most statistical software shows the p-value for a test. Now this is the likelihood of finding a more extreme value for the test statistics in a similar sample, assuming that the null hypothesis is correct. So it's difficult to calculate the p-value by hand. So as we have already seen in the figure, the test statistic is exactly 9.488, then the p-value will be p is equal to 0.05. Now, with the test statistic of 52.75, the p-value is very, very small. So in this example, most statistical software will report the p-value as p less than 0.0001. So this means that the likelihood of another sample of 10 bags of candy resulting in more extreme value for the test statistic is less than one chance in 10,000, assuming our null hypothesis of equal counts of flavors being true. Okay, so if we really want to understand, we should be very clear that what is chi-square distribution. So chi-square distribution is a theoretical distribution of values for a population. And how it is used? It is used for the statistical test where the test statistics follows a chi-square distribution. Two common tests that rely on the chi-square distribution are chi-square goodness of fit test and the chi-square test of independence. So coming to the chi-square distribution, it is a family of distribution. Each distribution is defined by degrees of freedom. Okay, we already have seen what it is. Okay, so here we can see in the graph, it shows three different chi-square distributions with three different degrees of freedom. Same data set, but degrees of freedom different, then the distribution will be different. So we can see that the blue curve with 8 degrees of freedom is somewhat similar to the normal curve, but it has no longer tail to the right than a normal distribution and is not symmetric. We compare the blue curve to the orange curve with 4 degrees of freedom. Okay, the orange curve is very different from a normal curve. So the purple curve has 3 degrees of freedom and looks even less like a normal curve than the other two curves. So the higher the degrees of freedom for a chi-square distribution, more it looks like a normal distribution. Now using published chi-square distribution tables, how to use them? So most people will use software to do chi-square test, but still many people will use statistics books to show the chi-square tables. So understanding how to use a table might be helpful if you are going to use it in future. So these are the steps given. We can find out the chi-square distribution. First, we need to identify the alpha value. And then each column in the table lists values for different alpha levels. Like if we have alpha at 0.05 for our test, then we will find the column for alpha is equal to 0.05. Then we will identify the degree of freedoms for the test, and then we will find out the rows in the chi-square table corresponding to different degrees of freedom. And most tables go up to 30 degrees of freedom. Now, then we will find the cell in the table corresponding to our alpha level and then degrees of freedom. And this is the chi-square distribution value. We will compare our test statistics to the distribution value and make the appropriate conclusion.